All right, so we're going to do a little bit of optics, and we're going to start off with the history of the theory of light. So the first thing we're going to talk about is the emission theory. So this is kind of an interesting theory. The emission theory, it was around for a long time because some of the famous scientists of the very olden days thought it was how light worked. So when other people would try to say, well, this doesn't quite make sense because all these revered scientists said, well, this is how it works. The theory on how light worked really didn't progress for quite a long time. So you'll see here, we've got someone like Empedocles. So he's 5th century before the modern era. We've got our Plato guy. Alrighty, you've heard of him. We've got Euclid, who was a brilliant mathematician. We've got Ptolemy, who is a doctor slash philosopher slash scientist, and we've got Galen here, who did a lot of work on the human body. He was kind of like an early doctor kind of thing. Alrighty, so all these people believed in this emission theory, and the emission theory, it's so crazy when you think about it. What they thought was that light came out of your eyes, hit an object, and then reflected back into your eyes, and that is how we saw things, that light was zooming out of your eyeballs, right? So that light leaves the eyes, hits the objects, and then reflects back into your eyes. So if you're looking at something, all right, there's an apple there, so light's going to come out of your eye and go back into your eye, and that's how you're able to see things. All right, but when you think about it, does that even make any sense at all? It didn't explain, like the other scientists were saying to people, well, this doesn't make sense of why you can't see in the dark, because if you go into a dark room, light should be able to come out of your eye, and you should be able to light up everything that you're seeing in the room, and it's not how it worked. But they said, well, there's a simple explanation for this. It's because light that comes out of your eyes is different than the light that comes off of a candle or the light that comes off of the sun. Okay, so they also thought that light from the candle or the sun was different than the light was emitted from the eyes, and that's how they got away with sticking with that emission theory for so many centuries. All right, so they were the first people who contributed to the light theory, but wasn't quite correct. Our next guy here, we've heard of this guy, Aristotle. He, of course, it's not a real picture of him, but he observed rainbows and contributed that rainbows are formed when the sun reflects off of raindrops. So he saw that the sun would break up into these different colors and form these rainbows. So this was kind of cool. And then we get to this next guy, Alhazen. So Alhazen, and there's all sorts of different spelling of his name, but he was prominent during the Islamic Golden Age. Now, during the 1100s, or during the Islamic Golden Age, which was part of the 1100s, or the 1100s were part of, the Muslim countries were so far ahead of the Europeans in terms of science and math and medicine, way ahead of people in Europe. And when the Crusades came through, when they were trying to spread Christianity all over, what happened was they killed all the scholars and the doctors and any of the educated people that had a whole pile of information. They went through, they burnt all the books that were in their libraries, destroyed all sorts of I'll just say like hospital type places and all that kind of stuff. But Alhazen, he was kind of a smart dude. So he figured out that this whole light theory was just complete nonsense. All right. So, and this was in the early 1100s. So we basically call him the father of modern optics. And what he said was, this is really kind of cool when you think about what he did in the early 1100s. He said that vision occurs when light reflects off an object and goes through our eyes. So the light is reflecting off an object. So light is coming from a different source, reflecting off of an object and coming through our eyes. And if you think about it, what he's saying is the vision occurs when light reflects off an object and goes through the eyes, and then he adds to it, the vision actually occurs in the brain. And he's absolutely true. Our eyes aren't interpreting what we're seeing. All our eyes are is a little opening for the light rays to go through. It's our brain that's actually doing the seeing. The brain is analyzing the light rays that are coming through our eyeballs, which is kind of a weird way to think about it, since we always say, oh, you know, we see with our eyes. Well, we don't. We actually see with our brain. All right, so now a number of scientists jumped onto the intelligence bandwagon, so to speak, and we have the intermission theory. And basically what happens in the intermission theory is the rays of light are bounced off of an object and then into our eyes, and then our brains are interpreting it. All right, so much different than the emission theory, which would be really helpful if we had emission theory if we had to go out in the dark. So our next scientist, or one of the many, remember there's lots and lots of scientists that contribute to any of these theories, just picking some of the more famous ones. So Galileo in the 1600s, he decided, here's a little picture of him, or painting of him, he wanted to know how fast light moves. Right? So form of energy, he wants to figure out how fast can it move, because they can figure out how fast sound travels. He thought he'll be able to figure out how quickly light travels. So what he did is he had his students, or two of his students, stand at the top of two hills, and he knew the distance between the two hills. Then they both had lanterns, and then Galileo was afar and watching them. So what he would do is one student would open the lantern, and Galileo could start timing and see how long it took for the other student to open the lantern. And the other student would have opened the lantern as soon as he saw the light from the first student. So obviously you can tell it's probably really, really difficult to figure this out. They weren't very accurate, but it was still kind of a neat way to figure it out. So here's a little diagram of what they did. So one student's at the top of the lantern, the other, or the top of the hill. The other student is at the top of the other hill. He knows the distance between the two students, or the two lanterns, all right? So all he needed to do was time it and take the time over distance, and that would give him his speed, all right? Again, not very accurate, but at least he was trying. It's kind of a neat idea. All right, so what is the actual speed of light? Well, in 1975, so what happens with scientists, they all get together, these big conferences, and they make rules up for everything. So we have rules for naming chemicals, we have rules for weights and measures, and all sorts of stuff. So in 1975, the General Conference on Weights and Measures recommended using the value of, I'll put it up here, 299,792,458 meters per second for the speed of light. So figure meters per second. That is so fast. There's no way Galileo could have ever figured that out. So if we put this in smaller terms, or not smaller terms, but easier to write down terms, we have 2.99 times 10 to the 8 meters per second, which comes out to be this many zeros. So 299 million. Oh, I always get this wrong. 299 million. Yeah. All right. So that's how many meters per second. And we basically round this up to 300 million meters per second. So we basically just say it's 300 million meters per second. Of course, if you're working for NASA, you probably use the exact right amounts. Okay. So the next thing is the electromagnetic spectrum. So you should have a handout of the electromagnetic spectrum. And we're going to talk a little bit about what the electromagnetic spectrum is. So basically, it's the range of wavelengths over which electromagnetic radiation exists. So, gee, we're using this term electromagnetic radiation an awful lot. And what the heck is electromagnetic radiation? Well, basically, it is just energy that travels and then spreads out. So there's a bunch of different forms of electromagnetic radiation, and we'll talk about what those different forms are and as you look at your diagram. So electromagnetic radiation is energy that travels and spreads out as it goes along. So your diagram is going to look different than this diagram, because I found that one that you guys have, and I thought that was a little bit more interesting, and it made this page too cluttery, so I just found a simple one for here, and then you have the one that's kind of got a little bit more information on it, which is, I think, quite interesting. So if you look on your electromagnetic spectrum, here's your different types of energy. We start down here, or I think yours is flipped, but it doesn't matter. We've got these short wavelength, high frequency, high energy rays on this side, your gamma rays. So these are the rays that would be released in a nuclear reactor, or if there was a nuclear bomb that was released. These little guys with their short wavelength can penetrate into cells. It can bash up DNA and cause illness or cause genetic problems. All right. Next to that, we have our X-rays. So here's your X-rays. These guys are pretty small too, and they're pretty high energy, which is why you don't run around getting X-rays, every week if you've got an ache or a pain. Really, really, really helpful. If you're worried about being exposed to radiation, if you're getting an X-ray, a chest X-ray is equal to a 4-hour flight. So as long as you're not going weekly for a chest X-ray, you're not being exposed to that much radiation. The amount of radiation you would get from a dental X-ray is equal to being outside for 1 hour. So if you're worried about that, just don't go outside for 1 hour when you would have gone outside. Here's our ultraviolet light. Here is our little visible spectrum of light. So this is the kind of light or energy that we can see. And we've got our infrared light here. If anyone has one of those warming lamps that used to be quite popular in bathrooms, they kind of, they're reddish colored and all they are is heat. They're heat lamps. Or if you've got things like turtles or lizards or anything like that at home that need some heat lamps, that's the kind of radiation that they're getting. Then we've got our microwaves, which bounces around the water molecules in our food to heat them up, and our radio waves. So these are long wavelength, they're low frequency, they're very, very low energy. So these do not have the capability of penetrating into our cells and causing cancer. So your cell phone, which works on radio waves, your cell phone is not going to cause brain cancer because those energy waves can't get into those cells at all. The 5G networks, not going to do anything. It can't penetrate into our cells to cause any damage. All right, but this is the little part here that we are going to be concerned about. Tiny little visible light. All right, so basically, what is light energy? Well, light energy is a form of energy that's detectable by the human eye. So it's the type of energy that we are capable of seeing. And how we get light energy is we have one form of energy and it's converted into another form. So if you think about a light that you may use, you may have a desk lamp. You turn your desk lamp on, we get electrical energy that runs through the wires, runs through the light bulb, and then next thing you know, you've got light that's glowing out of that light bulb. Right? So it's formed when one form of energy is converted into another. And if you think about something like a match, all right, with a match, you've got chemical energy that's converted into light energy. So, what are our sources of light? We've got all sorts of sources of light. Our light can be produced naturally, or it can be produced by artificial sources. All right, so produced from natural and artificial sources. Now, natural light is light that occurs on its own. So something like the sun or a star or fire, anything like that that produces its own energy is called a natural form of light. Oil lamps, if anyone's got an oil lamp at home, or they used to use oil lamps in the olden days, those would be natural forms of light. So natural occurs on its own. So for example, sun, fire, and oil lamps. All right, and our artificial sources, these are human-made sources of light. So something like our lamps. I'm trying to slow down here a little bit so you guys have time to write these notes because I realize I'm talking so fast. And again, if we were in class, I would look around, I'd see people writing like crazy, and then I'd slow down a bit. Alrighty. So we have another term here, luminous versus non-luminous. So a luminous object is any object that gives off its own light. So something like the sun, we would say the sun is luminous. It's a natural source of light, and it's also luminous. So luminous is any object that gives off their own light. For example, the sun, or a star, or a firefly. And a non-luminous object is an object that does not give off its own light. So something like the moon. The moon reflects the light from the sun, and that's how we see it, but it's not giving off its own light, it's just reflecting the light. Now, this spelling error has been on this slide. Thought I had fixed it last semester, but clearly didn't. But that should say its own light. Okay, so non-luminous is an object that does not give off its own light. Light. All right, next slide. Sources of light energy. So this is going to be a bunch of sources of light energy. It's going to seem like it's long, but it actually goes fairly quick. Alrighty, so sources of light energy. Our first source of light energy is if you've ever looked inside a toaster when it's toasting and you notice that the coils are bright orangey, or you've gone to make yourself some like craft dinner and you've turned the wrong burner on, or you forgot to actually put the pot on the burner, you walked away and you came back and the coils are really, really red hot. That's an example of incandescence. Some of you may still have incandescent light bulbs at home as well, where you can see the tungsten wire on the inside and it glows really, really hot and really, really bright. So that's incandescence. Incandescence is when you heat up an object enough to emit light. And we're going to have electrical energy that's converted into light energy. And in this example here, this is incandescent light. These are the kind of, and if anybody has an Edison light bulb at home, you probably have seen how the coils light up here and glow. All right, so this would be glowing, you know, white hot. And the incandescent bulbs also give off a lot of heat. They're they're not very energy efficient, which is why they were phasing the incandescent lights out. Okay, our next one, which you're probably somewhat familiar with, is electric discharge. So what we can do is we've got those gases. Remember those noble gases? They don't explode, they don't go on fire. They're all chill and relaxed because they've got a full outer energy level there. So we've got our helium, we've got our neon, we've got our argon. So what we can do is we can take those gases, put them into a tube or something, and then zap electricity through them, and those gases get really, really excited. And how they give off their excitedness is by emitting colored light. Alrighty, so we've got electricity that passes through a gas, and those gas particles emit light. So something like your neon signs. Now the next one is phosphorescence. I love glow-in-the-dark things, and this is phosphorescence. All right, so phosphorescence. What happens in phosphorescence is you've got these little chemicals called phosphors, and what they do is they absorb energy from another source of light. So, you know, if you have a little glow, something that's glow in the dark, you shine a flashlight or you hold it under the light. So while you're doing that, it's absorbing that light's energy. And then when you turn the light off, you can see the phosphors emitting that energy that they have absorbed from that light source. So they're pretty fun little things. So for phosphorescence, we emit light after another source of light has been shone on the object. All right? And that object, whatever it may be, contains phosphors. Here's a glow-in-the-dark bike. So phosphors are particles that get excited when they have this other light shone on them, and then they emit light. Now, the energy that they emit doesn't last a whole long time, but it's just kind of fun having the glow-in-the-dark stuff. And we can use these phosphors for our next source of light. So our next source of light is fluorescence. Now, if we were in class, we could just look up at the ceiling and look at the fluorescent bulbs, or a lot of your houses now have fluorescent bulbs. And if you've ever noticed with the fluorescent bulbs, they've got like a they're kind of cloudy. There's a coating on the inside of those bulbs, and that coating on the inside of the bulbs are phosphors. So again, they're the little particles that get really, really excited when energy is shined on them. It's not very good grammar, but we're working with it right now. So phosphorescence, again, phosphorescence occurs for getting light from another source and then emitting your own light. So emitting light while getting energy from another source. There's a couple of steps that happen here for fluorescence. And it'll make sense to you with why you have to throw away, or not throw away, but you have to get rid of your fluorescent bulbs at the hazardous waste site. So here's our fluorescent bulbs. As you see, they've got like a white coating on the inside, a whitish coating on the inside. All right, so you plug in your lamp or you turn the switch on in the classroom and the electrical energy zooms through these tubes. Alrighty, now these tubes are filled with mercury vapor. So, and mercury is not a very safe substance to have around, so this is why you need to take them somewhere safely to get them disposed of, because we don't want them to break and then release that mercury into the atmosphere. So the mercury vapor that's in those tubes gets all excited because of this electrical energy. Now, when that mercury vapor gets all excited, it emits ultraviolet radiation. So we can't see that type of radiation, but it is a form of electromagnetic energy. So it's going to emit UV light. So that mercury gas now emits UV energy. And what happens with that energy from the mercury vapor is it is absorbed by those phosphors, and those phosphors in return emit that light energy. Okay, so the UV now hits the phosphors on the tube, and just like for phosphorescence, those phosphors release all that extra energy as light. Okay, so the phosphors emit light. So a bit of a complicated process, but that's how it works. Now the next one again is fun. It's a fun one. Chemoluminescence. So what happens in chemoluminescence, you can see right here with this word here, chemi meaning chemical, luminescence meaning giving off light. All right, we're going to have chemical energy that's converted into light energy. So this is going to be chemical energy is converted into light energy. And it occurs when you have two chemicals react and they emit light. Now, unlike incandescence, this one is going to happen at a low temperature. Oops, let's see if it comes up. So this is low temperature. Incandescence, we have our toaster or our fire or the little burners on the stove that are glowing because they're at a high temperature. This is low temperature. Now, if we were in class, we would have examples of this, and I would ask anybody, do you know what a good example of chemoluminescence is? And we would all have some fun with some glow sticks. All right, but that's a great example of chemoluminescence. You crack that little thing on the inside, you mix the two chemicals, and you have this nice glowing, colorful thing the whole night long, and it's at a low temperature, so you're not like a little kid at camping burning yourself on something. All right, so bioluminescence, what bioluminescence is we've got a chemical reaction that happens in a living organism. And you probably have a great example already in your mind about bioluminescence. Bio meaning living, and luminescence meaning giving off light. So this is light being given off by something that's living. Again, we're going to have a chemical reaction that occurs in a living organism, which is producing light. So light produced by a chemical reaction in a living organism. And I'm sure a lot of you at this point, because if I'm in class, I'd say, can everyone give me an example? And everyone's going to say fireflies. So yes, fireflies are a great example of a bioluminescent substance or a bioluminescent organism. And the chemical that reacts in the firefly is called luciferin, and Lucifer from the devil, because the devil kind of glows. All right, so it's a chemical that produces light and it reacts with oxygen. And the really cool thing about this too is that 98% of the energy in this chemical reaction that's happening in that organism is released as light. So 90% of the energy is released as light. So it's kind of nice. So the firefly is having this chemical reaction and it's not like burning itself up as it's flying around, right? Most of that energy is released as light, and 2% a little bit of heat for it, which is great because it needs to have enough heat to survive. Alrighty, our next one is an LED. People are probably very familiar with LED, especially for computer stuff, or even this year there was lots and lots of beautiful LED Christmas lights out. They've really come a long way with really nice colors. So this is called a light emitting diode, which is what LED stands for. It's a semiconductor. We haven't really talked about semiconductors right now, but a semiconductor is a metalloid. So on the periodic table, you have metals and nonmetals, and then right where that split is between metals and nonmetals, you have metalloids. So these are elements that have properties of metals and nonmetals. So they emit, or they can transfer electricity, but they don't do it at a really, really high temperature like something like copper will do. So basically what these little LEDs do, these light emitting diodes do, is they emit light when electric current is passed through it again. So we're going to take electrical energy, we're going to put it through a semiconductor, which is going to allow the electrons to move through and then emit light, but not at a super, super high temperature and very, very efficiently. Alrighty, so those are different sources of light that we can talk about. Now, types of materials. This is going to remind you of grade 9 when we did physical properties. So types of materials when we're talking in terms of light. We can have something that is transparent, where light easily passes through. We also can call that clear. All right. We can have translucent, where you have some light that passes through. So if you think about a shower door or something like that, where some people have those frosted shower doors, so you get light through, but you don't get the images through. And we can have opaque, where absolutely no light passes through whatsoever. Ready? So those are the 3 types of materials that we're going to talk about when we talk about light. Now, what happens when light strikes matter? So 3 things can happen when light strikes matter. The first thing is, we talked about this a little bit already, is light can be reflected. So this is when light bounces off an object. And we're going to be doing a lot of bouncing light off objects. Hopefully we're back in class and we're using the mirrors. So if you think of a mirror, this is light bouncing off of an object. Light can also be absorbed. Oh, there, I got my example down. There's a mirror. Alrighty. So light can be absorbed. So anything that's not white is going to absorb that visible spectrum. So if you're wearing a black shirt on a summer day, all those light rays are being absorbed into that black shirt. Okay, so absorbed, it was when light energy is taken into an object. So anything that's not white is going to absorb it. Or we can transmit it. So this is when light easily passes through an object. So if you think about a nice clean window, we're transmitting our light. So transmitted, light passes through an object. For example, a window. We're just getting some terminology out of the way here, so we can move on quickly after this. So we can have different sources of light. If we have something like a point source, it literally is as simple as it sounds. A point source is a small concentrated source of light. So if you have something like a pen light, right, where a little pen light where you get a nice sharp little beam of light, that is a point source. An extended source is something that's a large source of light, where light is being given off in all sorts of directions. So something like your overhead lights in your house or at school, or if you have a candle that's burning and it's giving off light in all sorts of different directions. Alrighty? So a point source is a small concentrated source of light. Right? So for example, a pen light. And here's a little picture that went right over the words. And an extended source of light would be something like your overhead lamps or your overhead lighting in your house, chandelier, something like that, or a candle is going to be a large source of light. You're going to have light going out in all sorts of directions. So an extended source is a large source of light. For example, an overhead lamp or a candle. Now, what we used to do in the olden days is we would spend a day anyway, doing a lab of shadows, but you're supposed to have already done this before. But we're just going to review a little bit about shadows. You should have that on your sheet as well, this little diagram. So take a peek at that. You can write this right on there if you want to. So, there's a picture of my overhead light before I change slides. So a shadow is basically any area where light has been blocked by an opaque object. So area where light has been blocked by an opaque object. Obviously, because we get a shadow, it's because the opaque object doesn't let light go through. All right, and we got two different types. Normally I would ask you this, an umbra, which is the dark part of a shadow. And if you've ever noticed your shadows, especially if you're out walking outside and you're going in between street lights at night or whatever, you'll always see like a dark part of your shadow and then you see like a light part around the outside. That's the penumbra. So it's the light part of a shadow. And here on your diagram here, you can see the difference between the umbra and the penumbra. So if you're going to use an extended source of light, you're going to have light that's kind of scattered all over the place. The place where the light is completely blocked is going to be your umbra. So this is nice black shadow. And the spot where a lot of the light is blocked, but a little bit of light can still get through, all right, that's going to be the penumbra. Now on your diagrams now, and I'm going to put the links in here for you to watch the little videos on this, because it's kind of nice to remember, and we do end up with eclipses every now and then, so it's kind of nice for you to know what's actually happening in an eclipse if you've forgotten. I have to look them up every time there's an eclipse. I have to remind myself of exactly what's happening, because I confuse myself. All right, so for a solar eclipse, you should have this picture. In this particular case here, in a solar eclipse, we've got the moon that's in between the Earth and the sun. It only makes sense. It's just sometimes my brain doesn't, I make up stuff sometimes. Alrighty, so if you're in the path where you've got the total eclipse, you're in the part of the Earth where the moon completely blocks the sunlight. You're in the umbra part of the eclipse. And if you're in these other parts out here, you're going to be in the penumbra part of the eclipse, right? So the solar eclipse, we've got the moon in between the sun and the Earth. And we've got the penumbra, which is where the sun's rays aren't completely blocked. And then we've got the umbra, where the sun's rays are completely blocked by the moon. All right, so that's your solar eclipse. This doesn't happen very often. But we do end up with a lot more lunar eclipses. Okay, but if there's a lunar eclipse, chances are it's going to be cloudy, just like it was for those stars at Christmas time and the meteor showers and everything else. Anyway, so for a lunar eclipse, we've got the Earth that's in between the moon and the sun here. Alrighty, so we've got the sun here and we've got the Earth, and what you're seeing in a lunar eclipse is you're seeing the shadow of the Earth on the moon. All right, and then again, you've got the penumbra that's around the outside here, which we don't really see because we're not looking at, we're only looking at the moon. And we've got the umbra that happens here. Okay, last slide for today. This has been a long one. I hope you've taken a couple of breaks during this. If you haven't, I commend you. So the properties of light, this is our very last slide. So good for you if you've managed to stick through this whole entire thing. If you've taken a couple breaks, that's fine too. I kind of hope you have. So properties of light, we're not going to get very deep into this, but light has attributes of particles and waves. So light travels in little packages called photons, and they travel in a wave-like motion. Okay, so that's all we're going to say about this right now. You can take more of it when you get into physics. Light always travels in a straight line. So it's not like it comes down from the sun, does a little circle, little zigzag. It travels in a straight line. The only reason it's going to change its straight line is if we block it somehow or reflect it into another direction. Okay, and again, if you want to learn more about how light travels, watch yourself a video about quantum mechanics. I'm not going to assign one, just if you're one of those people who really wants to know more, you go right ahead. So for this long note, I know it's horrible, there's a couple of Quizlets that are set up to help you review, and then there's going to be a quiz on this. Okay, so that's going to be the assignment for this properties of light, is a quiz. Alrighty, so see you next time.